Hello, and welcome to today's problem 853 car fleet. So there's n cars going to the same destination along a one-lane road. The destination is target miles away. So we have target over here as a parameter. You're given two arrays, which are populated with integers, and they're called position and speed, both of length n, where position at a given index is the position of the index's car, and speed at a given index is the speed of the index's car in miles an hour. Okay, so looks like we have some constraints here. A car can never pass another car ahead of it, but it will catch up to it and drive bumper to bumper at the same speed. The faster car will slow down to match the slower car's speed if this happens. So the distance between these two cars is ignored, so they're assumed to have the same position. Okay, so we'll keep that in mind. And a car fleet is some set of non-empty, or like it's a non-empty set of cars driving at the same position and same speed. So a single car is also a car fleet as well. Okay, if a car catches up to a car fleet at the right destination point, it will still be considered as one car fleet. And what we want to do is return the number of car fleets that will arrive at that destination. Okay, so let's take a look at this example. We're given the target, the position, and the speed, and we know that like these are the positions and speed for a car at that given index. So we have like a car index 0, position 10, speed 2, etc., etc. And the output is 3 because the cars starting at 10 at speed 2, see over here, and 8, speed 4, become a fleet, meeting each other at 12. Okay. Let's go ahead and actually make a visual example of that first. So I'll go ahead and do that here. Okay, you know what? We'll erase this actually. Okay, so we know that basically the target is 12, so that means there's going to be cars at any number of positions up until 12. So 1, 2, 3, 4. Okay, so we have basically this like timeline, and we'll just like wrote like positions, and then from here we know that cars are at different positions within this line. So we have, let's say, okay, at index 0 it's at position 10 going at speed 4. So let's say like car at index 0 is going here at a speed of 4, right? Well, at a speed of 2. And the second car is going at 8, so it starts here, but it's that one's starting at position, starting position 8, and it's going at speed 4. So at index 1, we know this one's going 4 fast, this one's going 2 fast. As the next step occurs, like let's say like we have like another step to see what all the cars will look like as they go forward, we'll have 0 move forward 2 up to 12, and then 1 move 4 forward because the speed is 4 up to 12 as well. Now, this means that these cars are in the same fleet, which is why this is counted as an explanation. Okay, that makes sense. Okay. And okay, so the other examples, 0, we'll start off at car starting at 0. Yeah, car starting at 0 doesn't catch up to any other car because it just moves forward 1 each time, and it'll take like let's say like 12 steps in order. Let's see, because car 0 is going at speed 1, it'll take 12 steps in order to reach the very ends. Okay, so that makes sense. Okay, so one thing I'm noticing here with these cars is that it takes a certain amount of steps in order for you to be able to reach a target, for each car to reach a target. So, for example, in the case of the car at position 10 with speed 2, it takes about 2 steps. Well, it takes actually 1 step in order for it to reach the end. And for the car at 8 at speed 4, it also takes 1 step as well because it jumps straight from 8 to 12. In 1 step. This one takes 12. So, okay, now we know this information, let's think. Okay, so, so since a car can never pass another car ahead of it, but it can catch up to it and drive bumper to bumper at the same speed, what we know that, what we can figure out from this is that eventually, like let's say like one's like speeding up, and like eventually like it's traveling at a faster pace than the other one, but eventually it hits it, and then they both travel at the same speed. At that point, that's when they're both going to be equal to like the same fleet. So one way we can figure this out is, let's say like there's a car ahead, right? So the car at position 10 is obviously ahead of the car at position 8, right? At the very beginning. So if we move this to the beginning, this one starts at 10, and this one starts at 0 over here. So we know that these both start over here, and we know that this one takes basically one step. This one takes one step as well in order to make it to the very end. Like knowing this, we know that if let's say like the car over here, let's say the car at 0, if it ends up being a lot faster than this one, it'll have to be restricted to 1 at a given point, right? Because let's say like this jumps here, like to the very end, and then this one like jumps like way far ahead, right? Or like basically like it goes like faster. It'll be constrained because it can only go bumper to bumper with that other car. So let's say like one step, this one goes like 8, it can't do that, so it has to like be restricted down to here. We know that if a car is faster, will end up in same fleet. So if like eventually these two collide, then it'll end up at the same fleet. And we know that since these both well, we know that a car is faster, like we said before, if it takes a certain amount of steps in order for you to reach like achieve target or something. So if steps are equal or less than like a car ahead, then it's faster. Knowing this information, what we can do is we can utilize this in some way in order to figure out whether or not it's bumper, and then have that as part of the same fleet as well. Okay, so an idea I have right now in order to solve this would be to have a stack, right? So we would have a stack here, and as you traverse through the array, let's say the array of targets and like the positions and the speeds, what we would do is we would append the position and the speed onto the stack. So we have, let's say like we start off at position 10 at speed 2. That's the very first car that we start up. We need to modify this the position and speed in order to be a tuple like that. So traverse through like that. So we'll have like we'll have the cars. We'll have a cars array that will initialize to contain tuples of all cars. And then we append this to the stack, and from here what we can do is we can check, let's say like we add the second car at position 1, where the speed is 8. Oh no, speed is 4 and the position is 8. So we have this position and then speed. So we have position and the speed. So with this knowledge, we have the cars and we have the stack over here, and we have the positions and speed. We can tell, we can use this like the information we know here. If the steps are equal or less than the car ahead, then it's faster. So we can check to see whether or not the number of steps it takes for this one, for like the car at this position is compared to this one, and whether or not it's a greater or like equal or less than. If it is, that means it's both going to be part of the same fleet. And what we can do is remove remove like the element from the stack and count it as part of one singular fleet. And at the very end, what we can do is return the length of the stack in order to figure out what that like how many fleets there are. So okay, so one thing we also need to figure out, let's say the 10, sorry, let's go that scan 10 and 2. One thing we also need to figure out is how many steps it takes to get to the target from our current position. So we have 10 and 2, we have 8 and 4, and using this target, like we have knowledge of the target, the position, the speed. Okay, so in order to reach the target, you need to figure out what the difference is in between the target and our current position. So target minus position. And using this, we can divide this by the amount, or like by how far you go for each, basically each step. So for like, I guess like how many miles you go in an hour. And in that case, that would be the speed. So we can use this, and instead of having the position and the speed in the stack, what we can actually do instead is we can append this formula, like the result of this formula, into the stack. So it could, like in this case, it'll take like one step here, it'll take one step here, and because these two are equal, equal or like could be potentially like less than, then we know that it's the same. It's gonna be part of the same fleet, and we erase that from the stack, and we keep going on and so forth. Okay, so if this makes sense, I'll go ahead and begin coding up the implementation now. So basically what we start off with is a, we want to initialize the cars array. So we do cars, and to do that, we can do, let's say like the, to do that, we can have the position and the speed for position and speed in zip, position and speed. And the zip method is basically a list comprehension method in Python, which allows you to combine the array to have it like the example that we were talking about earlier, where you have the position and speed over here. So at the very end, this cars array will be populated with a list of tuples containing the position and speeds of the cars at like indexes of these given arrays. So after we do that, what we're going to want to do is we're going to want to loop through this. So for position and speed in cars, we want to append to the stack. So, we'll have a initialize the stack over here, containing the position and speed. So we want to have the stack over here, and we want to append, so stack.append to the stack, pretty much the formula we were talking about earlier. So target minus position divided by speed. Now, once we have this appended to the stack, we can go ahead and check to see if if the length of stack is greater or equal to 2, which means if there's 2 currently existing elements in the stack, and if basically stack at position -1, or I guess like stack at position -1, basically the topmost element in the stack is equal or less than, so it has to be like this. Yeah, equal or less than equal or less than the position at stack 2, so at like the second most element in the stack. If this is valid also, and stack -1 is less than or equal to stack at that second most one, then we're going to want to pop that element from the stack like we were talking about before, so stack.pop, and we're going to want to keep on going. And then at the very end, what we're going to want to do is return the length of that stack array. Okay, so another thing I noticed is we also have to check to see, we have to modify this, so instead of target position and speed is actually the position here, the speed here, and the target, which remains the same. Sorry, syntax error here. Cars.sort reversed equals true. We want to reverse this set of cars because we want it to start at the car at the basically at the very end, the last one, instead of the one at the very beginning, because you want to be able to check it for its behind, not for the one in front. So go ahead and run this now. Oh, reversed. Oh, right, reverse like this equals true. Okay, great. Yeah, so the time complexity of this would be O of n log n, because the actual operation of adding to the stack, etc., is O of n, but the action of sorting in reverse order would have to be log n, so we'll just have to append those together, and the space complexity is O of n because you're storing all the elements in the stack over here. So yeah, thanks for watching.